When we draw our Lewis structures, we're expecting to get to an octet, but there's some exceptions to that rule. We're not always going to end up with 8 electrons on it. Now let's see when those 3 exceptions occur. Now, one category is going to be electron deficient molecules. They have less than 8 electrons around their central atom. And the only 2 that can really do that, other than hydrogen and helium, which we know why they do it, they're so small, are going to be the 2 atoms that are a lot like that, beryllium and boron. Now let's take a look at them on the periodic table to have that emphasized. So here we have beryllium, and here we have boron. And those are going to be the 2 that we can have that weirdness happen with. I like to call them the devil horns of the periodic table. They do something funky. Why? Because notice what happens. They can end up with sharing, feeling like they're almost like a noble gas. These 2 atoms can feel like the noble gas configuration with 2 electrons. They do the duet thing. But here, in this row, beryllium also feels like it has a duet, right? It has the 1s and the 2s orbitals filled. It doesn't get the extra little bit of stability from filling up the 2p, but it doesn't really care about the 2p yet. It's still a really small ball of positive charge around the negative charges. So beryllium is pretty stable like that, with only 4 electrons total and 2 in its valence level, or octet level, whichever way you like to think of it. Boron, exactly the same argument for exactly the same reasons. Yeah, it's got that 5th electron, but once it's sharing, it can basically feel like it's got 4 again, because when it's sharing, it doesn't always have to hold that 5th one juggled around in a p orbital. So that's one of the reasons that they can feel so stable. Now, a second category are going to be odd electron molecules. Now, those are going to be weird. Those are going to be called free radicals. And free radicals will react immediately whenever they can find something, and it's going to try to pair up with things. One example of that would be the hydroxide radical, HO, and we do it like this. We just draw a single dot there. That's communicating that it's got an unpaired electron. An unpaired electron on a molecule, hyperreactive. Now, what's going to happen with those in our body? Well, notice that any time that it bonds with something else, everything else has even numbers of electrons, right? It pairs or bonding pairs. So basically, this electron is going to be passed around like hot potato. And so you might say, wow, the only time it's ever going to be neutralized is when it finds another radical. And that's true. That would be one way for it to do it. But there's one other time that it can do something and neutralize out. And a good example of that would be when it finds a metal. If you've ever used peroxide to get a blood stain out of fabric, peroxide is actually HO, has a single bond here, and when it breaks apart, you can have one of each of these fragments taking one of those electrons from the bond. You end up with 2 hydroxide radicals. And so what can happen? When it finds the iron 3+, the orange-ish red-colored iron in your blood, it can donate an electron, or actually, let's see, 2+, 3+. Yeah, it can donate an electron to the 3+, become 2+, and now iron is 2+. It's blue, a very pale blue. It's the blue color you see in your veins of your arm, but it's not very dark. It's just that it's very concentrated in your arm. Best of all, that one doesn't stick to fabric very well, so it just rinses right out of your fabric. That's what you're doing when you use hydrogen peroxide to rinse out a blood stain. You're just using hydroxide radicals to do some sort of radicalized reaction. It reacts immediately. In the process, that ends up forming water and oxygen bubbles. When you see the bubbles coming off from hydrogen peroxide, you're not actually seeing the cells themselves dying. What you're seeing is the generation of oxygen from the radicals reacting with everything in sight. The radicals reacting with everything in sight is what killed those bad cells and the germs and viruses and other nasties. Now, that's a bit of a tangent, but I really wanted to hammer home the weird category of radicals. We don't work with them very often in chemistry. One, they're very hard to draw a lot of the time. They really are counterintuitive for us, and we don't end up using them a lot at this level of chemistry. But we hear about them all the time, and the coursework that you may be going on to with this course, they may use it quite a bit. Things like biology, biochemistry, these courses typically end up bringing up radicals a lot more often. So be aware of that. That's the 2 ways that you can end up having a radical neutralized back out, either finding another radical and binding with it, or interacting with a transition metal. Now, our third category is one that we're going to see a decent amount in chemistry, especially because it appears in one of my favorite ions to give people as an example of just about everything, the sulfate ion. Sulfate ion's got it all. And why? Because it's got the expanded valence shell as a possibility. So when your central atom has empty d orbitals, it can use those to have more than 8 electrons there. Let me show you what I'm talking about here by coming to the periodic table. Okay, so here on the periodic table, I was just bringing up sulfur, right? Because in the sulfate ion, we have SO4 2-. Sulfur is right here in group 6. It's going to have its 6 outer shell electrons. But here's where things get really fun. It's going to be at 3D. In fact, here, let me click on it, and it should show up right here. It's going to be inner shell like neon, 3D2, 3p4. The d orbital still exists and is still at the same radius, but we don't get to fill it until we're at a lot higher energies, right? We're not going to fill the 3ds until we're down here in this set of atoms, the transition metals. Well, but that doesn't mean that the empty orbital ever disappeared. If we're using my silly analogy of being like dorm rooms, if they close one of the floors in the dorms because they don't have enough people living there, the floor doesn't disappear. It's still there. Well, that's what we're talking about. And if you need to, you can move people into that. And it turns out it's energetically favorable enough and at a similar enough radius that it can do that. So sulfur is a great example. So everything in this segment right here is the first time you have d orbitals around, and everything coming down in this range can do the same trick. So these ones are allowed to do the expanded octet. Sometimes you're going to find that you have more than 4 bonds for these things. Let me show you what I mean. So if I'm talking about the sulfate ion, and I'll shortcut straight to the answer on this one. I won't worry about going through all the details. We'll see that one later. We'll get something like this. How many electrons does sulfur have? Well, it's going to have 1, 2, 3, 4, 5, 6 electrons to call its own. It's got more than 6, though, if you're counting your octet. You've got 2, 4, 6, 8, 10, 12. You're going to have 12 electrons that sulfur has access to. I'd say 12 is greater than 8. And that's what we're seeing here, is it's breaking it by using the expanded valence shells. I like to jokingly say that this is like using the chipmunk cheeks to carry around some extra nuts or electrons.